This is Duane Lewellen again with the Smart Building Center to get into the details on the Seattle Building Tune-Ups Assessment. We're going to start with the HVAC, which is primarily focused around scheduling, equipment scheduling, set points, functional testing, and maintenance. You'll notice also on the slide the tune-up rule. So if you have a copy of the Seattle Building Tune-Up Ordinance and the mandate, those numbers there identify to the assessment elements that are listed in that. And then if you're reporting your tune-up requirements, tab G is on the Excel form is the tab that we're going to be going through. So there are 11 HVAC assessment elements that have required corrections. And so these are all elements that if you find correct deficiencies and corrective actions, they shall be completed in order to comply with the mandate. We'll go through each one of these in more detail, but these are the 11 required assessment elements. These are going to be those items that are highlighted in green on the tune-up report, and so we'll go through each one of those individually. So equipment scheduling. As noted in a previous section, Pacific Northwest National Lab has looked at over 100 buildings, and this is by far and away one of the biggest opportunities for savings in existing buildings is just to review the operating schedules and adjust as required for the actual occupancy patterns. You know, occupancy changes over time, tenants come in and move out. So you're going to have to interview the occupants, gather building occupancy schedules and use patterns, review the actual thermostat schedules or the scheduling for equipment in buildings without building automation systems, in buildings with building automation systems, then review this program scheduled settings into the BAS system, or what's required in the lease for the tenants, and making sure that those schedules match. So that's a fairly easy one to verify. That can be either verified through the BAS, but you could also use trend data if you have access to trend data. So setting up a trend, for example, here's a trend of space temperature off the building automation system and over a week period or so, and I can tell you what time the system starts, what time it stops. Other good items to trend for scheduling is duct static pressure. That will tell you exactly what time the system is turned on and what time it's turned off. Or alternately, you could use a data logger. For example, a motor logger on the main supply fan or on a terminal unit fan or on a pump that will tell you exactly when that system is started and when it stops. So through trending and then verification of the occupancy schedules, you can compare the operation of the system to the occupancy and make any recommended adjustments if there's an opportunity to tighten the schedule or make other adjustments for holidays or other types of things. Set points. You need to review the set points and adjust or optimize for efficiency. You need to use your judgment here. So zone temperature set points, we talked a little bit, or I've spoken about dead bands, which is the difference between heating and cooling set points. So in buildings that have systems with heating and cooling, we want to make sure that there's adequate dead band. The standard recommended in the industry is 5 degrees. So 70 degrees for heating, 75 degrees for cooling, but use your judgment there just to try to minimize if there's very little deadband or minimizing opportunities for problems with simultaneous heating and cooling. Discharge air temperature set point, if it's a multi-zone system and you've got discharge air temperature control, is that set point reasonable? Discharge air pressure set points often are higher than they need to be. So again, use your judgment. You can maybe find the original design documents or the sequences of operation to let you condenser water supply temperature set points. Does it make sense? Does it meet generally accepted industry standards? Same with economizer changeover. You're going to need to determine what kind of economizer control that they're using and whether it's dry bulb, differential dry bulb enthalpy, differential enthalpy, and see if those settings make sense. and that they're getting full use of economizer cycles for cooling. It's the first stage of cooling. If there's demand ventilation, which is using carbon dioxide to override the minimum outside air to control the ventilation based on actual demand in a space, then are those control settings appropriate? ASHRAE recommends, ASHRAE 62.1 recommends that you maintain no higher than 700 parts per million above ambient for your CO2 levels. And so are you overriding, are you allowing it to get above 1100, or are you under ventilating on that? During the heating months and the cooling months is a great time to check demand ventilation, because when we use economizer, we overventilate, but because we're using economizer for cooling, so that's fine. But if you do have demand ventilation, are the set points correct? Building pressure set points, typically on multi-zone systems with variable volume, we control building pressure to no greater than 0.05 inch positive static. But if you do some trending and you find that the building is negative or overly positive, then you can review those set points. Outside air temperature lockouts, primarily for boilers, chillers, heating water pumps, cooling water pumps, condenser water pumps, cooling towers. Are those, do we have an overlap there where we have simultaneous heating and cooling, or at least the systems are enabled and capable of doing that? Does that make sense? And then general set points for miscellaneous equipment. So elevator machine room temperature. Are you overcooling the elevator machine room? What does the manufacturer recommend as a maximum temperature? Data rooms, garage exhaust. If you've got underground or enclosed parking, you more than likely have some kind of mechanical exhaust system that we want to basically maintain so that the parts per million, carbon monoxide parts per million, doesn't exceed 50 parts per million as a maximum. Typically what I've seen in there is they will initiate a fan or speed up a fan or turn on fans when at 35 parts per million, and then turn them off when it drops below 25 parts per million. So again, use your judgment. Or do the set points make sense? Are there any opportunities for savings in fine-tuning or optimizing these set points? If there's any reset schedules being deployed, are those reset schedules, do they make sense? Have they been overridden for some reason? So if you're resetting boiler loop temperature based on outside air temperature or heating demand, do you have a condensing boiler or conventional boiler to see how aggressive you can be with those resets? Are you resetting chilled water temperature? A common practice is to reset chilled water temperature 5 degrees or so. So as the cooling demand increases, you set the chilled water loop temperature down. Same thing on, and then we've got pump differential resets. If they're doing this, if they're not doing this, this could be an opportunity, but you're not required to implement this if they don't do it. But if they have the capability of doing it and they're not taking advantage of these savings, then we want this corrected and implemented. And then duct static pressure. In newer buildings, the newer codes now require on larger systems that duct static pressure and large pumps be reset based on demand. So do they have duct static pressure reset? If they do, are they implementing a reset schedule that optimizes energy efficiency? Again, use your judgment as to what these set points and schedules should be. Optimum start controls. A lot of buildings, even buildings with programmable thermostats, have the capability of having the computer start the building rather than the occupancy schedule. So we want you to answer a question. Do they have the capability of optimum start? Yes, no. If they do, are they implementing it? Are they using the optimum start function? If they are, great. Make sure that we talked earlier about scheduling, that the equipment schedule matches occupancy. But then let the computer determine when to start the system. And then these optimum start strategies, both in programmable thermostats and in DDC systems, will learn over time how long it takes to recover from a night setback or a weekend setback or a holiday setback. And so let the computer decide when to start the system. We just need to tell the computer when we want it to be up to temperature. When does the occupancy period start? Let the computer decide what time to start it. Are the controls functionally working, and are they calibrated? Recognizing that you could have many sensors in a building, one for each zone. The ordinance wants you to look at your critical sensors that initiate control action, and just verifying that they're functioning. One, and you could look at your BAS system and whether they're accurate. And if they're not accurate, they need to be replaced or calibrated. So here's some of the sensors that we want you to verify that they're functioning and they're calibrated. Obviously, outside air temperature. Outside air temperature initiates a lot of control action, whether it's hot boiler lockouts, chiller lockouts, economizer, resets. So we want to make sure that's accurate. Discharge air temperature. So hot water loop supply and return temperature, chilled water loop supply and return temperature, carbon dioxide sensors if you're using demand ventilation, condenser water supply and return temperature, and duct static pressure. So just making some static measurements and comparing that to the building automation system readings, or logging some of these conditions over time and then comparing that to the building automation system and making sure that these critical sensors are functioning and that they're calibrated. HVAC controls functional testing. Probably of all of the individual things, this may be the part of the tune-up that you spend your most time on. For those systems that are in your sample size, you're required to verify that they're functioning properly and that they're functioning properly in their different modes of operation. So for example, in the occupied mode, is the fan running on a call for heat? Is heat supplied on a call for cooling? Is cold air supplied? And then what those settings are. So functionally testing that. If there's economizer cycle on that, then initiating the economizer cycle and verifying that you have the capacity to bring in 100% outside air for cooling, and also the relief system for that is working properly, whether that's barometric relief or some sort of powered relief where you're mechanically exhausting the relief air from the building. In the unoccupied mode, we want to make sure that the fan is off and the isolation dampers are closed. So whether that's the relief air damper, the outside air damper, we want to make sure that those those dampers are closed and tightly sealed and the system is off, and that the setback, this would be a time to verify and look at your setback temperatures. If you're implementing warm-up cycles, then verifying that during the warm-up cycle, the outside air damper is closed, so you're using 100% return air until the building gets up to temperature. It's fairly common to initiate ventilation up to a half hour before occupancy, so you can start ventilating the building a little bit of primary just to provide some fresh air before occupancy, and normally about a half hour is what's used on that, and that's fine. But if it does have a warm-up cycle, if you have any overrides, if the system is overridden on the weekend, do the overrides work? Are the overrides limited to a time limit? Is that functioning correctly? Any other modes of operation that you may have on there, you'd want to test it. So for that sample equipment, this is going to be the bulk of your time with the controls, with data loggers, initiating control action, and verifying that it's functioning correctly. Simultaneous heating and cooling. We want you to identify if there's any opportunities to minimize simultaneous heating and cooling. So your work in this section is going to depend on the type of system that you have. We're looking for opportunities or instances where, for example, you've got perimeter heat, conductive heaters, hot water heaters that are operating at the same time that you're cooling. So there's no lockout between those. Or you've got large open spaces served by multiple air handlers, and there's no interlock between the air handlers to prevent simultaneous heating and cooling. So the classic example of the large auditorium space or a sales area on a sales floor where you've got multiple single zone package rooftop units, and they're being controlled by a thermostat, and you have the potential of one being in the cooling mode and one being in the heating mode at the same time. So if you identify that, we want to, and then also heating and cooling temperature lockouts. So lockouts between the chiller and the boiler so that we prevent any simultaneous heating and cooling. So if you identify that, and we want you to adjust the control sequences, implement lockouts, expand dead bands to minimize these instances of simultaneous heating and cooling. Another required element is the general condition of the HVAC system. So as you're going through and observing these systems, if you find dirty equipment, dirty filters, disconnected ducting, blocked or restricted grills, coils, or strainers, then you shall fix that. You shall clean or replace the filters. You shall repair damaged equipment. So if you discover that the air handler belt is broken and the air's not moving, then you shall fix that as part of the mandate. Missing or damaged panels, access doors or seals, missing or damaged equipment, damaged or inoperable dampers and valves, these all have to be repaired. So this is a mandatory element. Often you can't complete your tune-up on the other items in terms of, like, for example, economizer. If you discover that the damper is not working properly, it's inoperable, then you're going to need to fix the damper in order to functionally test the economizer, or get equipment up to speed. So just some examples here: jammed, frozen dampers, disconnected dampers, wired boilers. So a big part of the tune-up and what you're going to be doing is looking at dampers. Are they operating correctly? Are they functioning correctly? When they're closed, are they tightly closed? When they're 100% open, are they 100% open? And so verifying that that equipment is working properly. So the items that we covered, the 11 items that we just covered, are all mandatory items. If you discover deficiencies in your assessment, you have to correct that assessment. The next 8 items we're going to look for are voluntary. Voluntary means that the owner does not have to complete these, the building owner does not have to complete these in order to be in compliance with the mandate. However, the tune-up specialist is required to identify these voluntary corrective actions as they go through the building and inform, or at least notify, the owner that there are some additional recommendations for the tune-up for implementing best practices. And there's 8 here, specific recommendations for HVAC. Air balance issues, you don't have to do a detailed air study of the building, but if you note any indications of significant air balance issues, so negative pressure in the building, whistling air velocity, whistling through the doors, comfort complaints due to air balance issues, then we want you to recommend rebalancing those areas where you feel that there's significant efficiency or comfort improvements can be achieved. So perhaps an area that has inadequate airflow, that could be an example. Cool lobby, often in high-rise buildings, there's the symptom of a cool lobby because when the systems at night or when their main air handling systems are off, a stack effect and a variety of other things create a negative pressure in the lobby, which draws cold air in through the doors. So, if you note those kinds of things, we want you to put that on it's a voluntary action, but we want you to inform the building owner. Excessive ventilation rates. You do not have to adjust ventilation rates, but if you find excessive ventilation rates, we want you to inform the owner that there are significant savings that could be achieved by adjusting ventilation rates. So what are the examples of that? If you see outside air damper minimum positions fairly high, above 30%. Now that may be okay. Maybe that system is acting as somewhat of a makeup air unit for a system, so you have to bring in a lot of outside air, or it serves a space that has high density, like an auditorium or a conference room or something. That may be perfectly fine. But if it's a typical office space with office occupancy, minimum outside air of 30% is anything over 30% is pretty high. So that may be correct. You may want to look at that, go into that in more detail. Same thing on minimum primary air for VAV. If you see that the minimum primary air position is greater than 30% of the design CFM, that may be worth further looking into. Often What happens in buildings is tenant improvements are completed or there's changes made, and very rarely do people go back and adjust the VAV terminal box for the new occupancy. So that VAV box may have been serving a conference room and needed to have a high minimum CFM, but now it's been converted to offices, and you can reduce that to 20%. That reduces reheat energy. Or overcooling of the space. Low CO2 levels when operating at minimum damper position. So you can log CO2 levels and see that they're tracking with outdoor air CO2 levels. Excessive building pressure is another indication of excessive outside air, bringing in too much outside air or not having enough relief in the building. So if you see any of these symptoms, then you can recommend that if you indicate any indications of excessive ventilation, make analysis of the ventilation system if warranted with the owner and follow up. The owner could then maybe look at some of those areas where they see that there's excessive outside air position or minimum damper and correct it. It is a voluntary item, but if you discover this, then you need to inform the owner of the opportunity. Multi-zone systems with rogue zones. A lot of the larger office buildings use multiple zone systems like variable air volume. So central station air handlers serving terminal units. Often, there's a variety of spaces that are served by those air handlers, and a common opportunity for energy savings is to reset the discharge air temperature based on load. So typically the generally accepted discharge air temperature for cooling is 55 degrees, but there may be times of the year when you don't have a high cooling demand, and you can reset that 5 degrees higher up to 60 degrees. That reduces reheat, energy required to reheat that. It takes more energy to heat 55 degree air up to 90 than 60 degree air up to 90 degrees, and so that minimizes or that reduces some of the energy used for reheat. However, if you have a zone in the building, or if you have a space that needs that 55 degree air, it's at full cooling all the time. For example, a dispatch center in an office building running 24/7. Now I have to basically run my whole building system 24/7 to serve this dispatch center. So maybe there's an opportunity to serve that data center or that dispatch center with a separate HVAC system or a data closet. Probably the most common application we see is a VAV system that's serving a data closet or a data room, and that room is driving the reset temperature for the entire building. It needs 55 degree air. So if you believe that you could serve that data room with a separate system, or resize the VAV terminal so that it can cool at 60 degree air rather than 55 degree, that it can meet its cooling loads using 60 degree air, that will allow the entire central station air handler to reset its air and save energy that way. So either isolate the zones or upsize the size of systems for the zones to allow the resets to occur. We're finding that a lot of buildings have the capability for reset, but they're not using it for one of these reasons. On the voluntary side, on the HVAC practices, these are voluntary actions, but something that's important for the owner to know that if you had to replace dirty filter strainers, or if the overall condition of the HVAC system is poor, then recommendations to adopt some maintenance protocols per ASHRAE Standard 180. So ASHRAE Standard 180 has fairly specific guidelines on the frequency of maintaining equipment, whether it's lubrication, filters, keeping equipment clean, replacing missing or damaged duct and pipe insulation if you find it, or leakage, or if equipment's at the end of if it exceeds standard maintenance practices, so you have to replace the equipment. You can't just replace the damaged panels, or you can't just replace the missing or damaged insulation. Then that's a voluntary action, but we want the owner to be aware of that. And then if the equipment is at the end of its service life, then we would recommend that they adopt some sort of equipment replacement plan and schedule. So for example, a hotel that's replacing the guest room units, having some schedule out that they're replacing those over time. So just giving them notice that they're going to have to, that their equipment is at the end of its life, and that you recommend replacement in the future.